Okay, question 1 of the Year 11 mock for January. 3 differences between radio waves and sound waves is our first question. Easiest thing really is to look at the mark scheme and have a look at what you could have said. Sound waves are longitudinal, but radio waves are transverse is the first thing. Sound wave being longitudinal is just a fact for you to remember. Radio waves being transverse is something you can remember from the fact that radio waves are part of the electromagnetic spectrum, and therefore all of those waves are transverse, so radio waves must be transverse. Sound waves need a medium, but radio waves travel through a vacuum, so radio waves don't need particles, they can move through a vacuum, again because they are electromagnetic waves. Sound waves are vibrations with particles, they need particles to move. Sound waves have a much lower velocity than radio waves, that is certainly true. Sound waves, you're looking at around about 340 meters per second for sound. For radio waves, you're looking at something rather larger. That's 300 million meters per second, or 3 times 10 to the power of 8. That is the worst 8 in the world. Let's try that again. 3 times 10 to the 8 meters per second. They're travelling at 3 times 10 to the 8 meters per second because they are radio waves and therefore they're part of the electromagnetic spectrum. So they all travel at 3 times 10 to the 8 meters per second because that is the speed of light. They have lower frequency or greater wavelength than radio waves. Here's the thing, that's not really true. Sound waves do in general have a lower frequency. You're looking at 20 Hz to 20 kHz for sound, whereas for radio waves you're looking perhaps broadly in the range between 3 kHz, but then up to you're looking at hundreds of gigahertz as the top end of the frequency. So sound waves in general have lower frequencies. Greater wavelength, not so much. Radio waves can have wavelengths that are in the kilometre range. If you look at sound waves, and you can actually work this out for yourself, which is a fun little thing for you to be able to do. You know the wavelength equation, or the wave equation says that C equals F lambda. So if you want to know how long the wavelengths of sound are going to be, we can rearrange this equation by dividing both sides by F. C over F is equal to lambda, so the wavelength is the speed over the frequency. So if you want to work out the range of sound wavelengths, it's going to be the speed, which is 340 meters per second, divided by the wavelength, the frequency, which we said was 20 Hz would be the lowest frequency we have, so you could work out that. The highest frequency we have is 20,000 Hz. So you could work out those two calculations. That would tell you the range of frequencies that you're, or the range of wavelengths rather, that you'd be calculating. You get between 17 meters and 17 millimeters respectively. So yeah, I'm not quite happy with that part of the mark scheme, to be honest with you, but the real thing won't have that kind of ambiguity in it. And finally, sound waves are vibrations, but radio waves are electromagnetic waves, which kind of links in with this idea that the sound waves need a medium, but radio waves don't. They travel through a vacuum. Question 1b. Which of the following doesn't use microwaves? It's the TV remote control. You know that because it uses infrared, the TV remote. Speed camera uses microwaves bouncing off whatever it is that they're measuring. Wi-Fi, mobile phones, again, they both use microwaves to communicate. So it's D for that one. TV remote control. Question C. Microwaves are used to send and receive television signals from high orbit geostationary satellites. This is the exciting moment where we bring in a picture. You need to describe why microwaves rather than radio waves are used. It becomes clear when you look at the diagram. You would have seen something like this in the textbook. So microwaves just go straight through the atmosphere, straight through to the satellite, and they can come back. Radio waves don't. They reach a part of the atmosphere called the ionosphere, and they bounce. Or to be honest, more accurately, they refract. So they change direction, they curve downwards like this. So this is quite a useful thing. for radio waves, because it means that you can send this signal here from this transmitter all the way to this receiver, and you'll notice that they're not in a line of sight to each other, so you can get around the atmosphere like that and back down, so you can send a signal without it having to go straight through the Earth. But when it comes to sending signals to satellites, you're not going to want to use radio waves, you're going to want to use microwaves. So there's your answer, just to show you the mark scheme for that. Radio waves won't reach the satellites from Earth, 1 mark, because they're reflected by the atmosphere, 1 mark. You will get the mark if you said refracted as well. It's technically better because you've got that kind of curving kind of effect going on there. Describe the significance of microwave radiation in the development of a theory of the origin of the universe. Let's switch tabs on the phone. There we go. So we're talking basically about this. There we are, from Wikipedia. This is, sometimes it's been described as the oldest photograph of the universe. This is all of the blotchy area that you look when you look at the entire sky. You see that there are some areas that are producing more microwaves, some producing less microwaves, but overall there's microwave background radiation. So the question is, what does that actually do in terms of our understanding of a theory of the origin of the universe? The key idea is this, that the Big Bang Theory predicts that this leftover radiation would be leftover from the Big Bang, and the other big theory at the time, steady state theory, did not predict that this background radiation would exist. So the fact that we've detected it suggests that the Big Bang Theory is correct and steady state is not correct. So you get a mark for saying we discovered the cosmic background microwave radiation, which, you know, is fair enough because they haven't mentioned background as part of the question, so you're not really restating the question to mention we discovered it in the background of the universe. 1 mark for saying you could explain that as resulting from the Big Bang, and 1 mark for saying you can't explain that with steady state theory, and you get a maximum of 2 out of those 3 possible points for that question. There you are, that's question 1.